Hello everyone. In this video, let us try to solve the problem that we saw in the last video. So the problem, let me redefine the problem first. So the problem was this particular buffer node was seeing a length of wire which is equal to L by 4 plus L by 4 plus L by 4 plus L by 4. It's roughly equal to L. It's not exactly equal to L. It could be slightly less than L because this piece of wire is common between these two nodes, but roughly L length of wire this particular node was seeing. In contrast with this particular preceding buffer which was seeing only L by 4 amount of wire. And basically the length of wire immediately gets converted into a capacitance value. So the load that this particular node is seeing is pretty huge. So what we'll do is we'll take this section of the circuit and try to analyze it separately. Let us try to begin with it. So at this particular node, at this particular node, you have a fan out of 4. When I say a fan out of 4, it means that this particular node is driving around 4 devices. So 4 logic gates this particular node is driving. If this particular node was driving 2, so we would have told fan out of 2. So in this case, the fan out is 4. So what we'll do is we'll take this section separately and we'll bring it over here and try to analyze it. So let us make some assumptions over here. So let us put some capacitance, some real capacitance over here and give them some name. So let's call this as C1, C2, C3 and C4. So C1 is basically, so when we say C1, this particular capacitance consists of this complete length of the wire capacitance and plus the input cap of this particular flop. Similar thing goes for C2, for C3 and C4. The reason we have tried to distribute it, we have to try to understand what amount of cap that each and every node is driving. So that's why we have done this distribution. So C1 will be this complete wire cap plus plus the input cap of the flop. Similar goes for C2, this complete wire cap plus the input of the flop 2. Similar goes for C3 and the same for C4. So let us try to do this and let us assume some numbers. So let's say C1, C2, C3, C4 each are of 25 femtofarads each. If we try to use these numbers, so the solution that we are trying to bring about over here becomes more practical. So it's close to a practical scenario. So let us try to assume these numbers 25 femtofarads. So if we try to make this particular assumption, this particular node A is actually seeing an amount of capacitive load that is actually equal to 100 femtofarad. So it's basically an addition of all this particular capacitor. It's C1 plus C2 plus C3 plus C4. So 100 femtofarads in a real scenario is a huge number. So roughly, if you go by standard specifications, the amount of capacitance that a clock node should be seeing is roughly around 50-60 femtofarads. These are the standard specifications that is present in VLSI industry, but in this case the node A is seeing a capacitance which is 100 femtofarads, and this number is really very huge for a clock node. So what we'll do is we'll try to find out some solution so that the node A sees a less amount of load. So let us try to find out some solutions over here. So what we'll do is one of the best solution is how about creating a buffer tree at node A. So this particular buffer tree that we will try to create at node A will be slightly different than the tree that we built over here. Over here, the tree that we built was in a linear fashion. We were placing buffers at equal distances from each buffer. But over here, the buffer that will be the tree that we will be building, that will be more of hierarchy. So let's see what are we trying to do. So before even looking into the solution, can you think of some solution that could be applicable on this thing as well? So let me give an analogy over here. Let us try to assume this particular thing, this particular load is nothing but a huge cupboard that you need to push. So if it is not possible for a single person to push that cupboard, what we do is we bring along more persons to push the cupboard. So this is a very simple analogy. So basically what what we'll be doing is we'll bring in some more persons, we'll bring in some more buffers to push the load. So something like this, we'll try to break this particular thing and we'll try to introduce one buffer for a pair of each flops. So like this, so you have this particular buffer which is trying to push a pair of flops, and this is one more buffer which is trying to push a pair of one more pair of flops. So let's say this was the cupboard, and initially this huge cupboard was being pushed by a single person. Now what we have done is we'll create a group of persons who are going to push this cupboard. The analogy remains as simple as that. So now each and every person will not be seeing a huge amount of load, but will be seeing an amount of load which is like quite acceptable and quite within the acceptable limits of this particular buffer nodes. So let us try to see that. So at node A also we will be let us put some terminologies for each and every buffer present over here. Let's call this as cbuff1, this is cbuff2, and the original C1, C2, C3, C4 still holds the same. So and let us assume that the clock buffer 1, cbuff1 will be 30 femtofarads and cbuff2 is 30 femtofarads. So effectively at this particular node, the total capacitance that this particular node is seeing is 60 femtofarads. Is basically cbuff1 plus cbuff2. Then the capacitance that is being seen at node B is C1 plus C2 50 femtofarads, and the capacitance that has been seen at node C is again 50 femtofarads. It's like C3 plus C4. So these numbers, if you actually compare with the standard numbers, these are pretty much very close to the standard numbers, and it will ensure a proper waveform at the output. So the waveform won't be this bad, and waveform would be pretty much what we send at the input. So what we'll do is the next thing that we'll be doing is we'll be sending the waveform. We'll sending a similar kind of waveform at the input and see at each and every node how the waveform looks like. So this is the waveform that we were trying to analyze, and that we were trying to propagate through a clock tree and trying to achieve the same kind of waveform at each and every clock endpoint. So this is what has driven us to do these experiments. Let us try to propagate this particular waveform. So it propagates through the first buffer, and the waveform that you see over here is this one, which is pretty much close to what we send at the input. So now this waveform is basically a function of the capacitance that it sees over here. Right now it sees a capacitance which is 60 femtofarads, which is pretty much a standard number, and so the waveform looks very much close to what we sent at the input. Next, this waveform will propagate through this buffer and this buffer also, and let's see what will the waveform will be getting at this node A and node B and node C. So this is the one. So this particular waveform, which is the one that is being sent at this 4 clock endpoints, and this is the one that we actually started with, and this is the one that is actually expected. So instead of a waveform like this, we will be getting a waveform with a much better slew, and the waveform also matches with the one which we had sent at the input. So this is basically the solution that we are that we have brought it over here. Again, it is again on the cost of the area. We are spending some extra amount of area, we are spending some extra amount of route, but to get a very good waveform, to get a reasonable waveform. So this is a must. So there are a few things which is must. So you have to spend some amount of area to get a waveform like that. There is a penalty that you are going to pay, but in return you will be getting a waveform which is much close to the one which we are sending at the input, and a better performance. So there is always a penalty, but what you achieve from that penalty is a very good thing. So it's okay to pay that penalty. So next what we'll do is before moving forward, we have to derive some observations out of this particular clock tree, which I will be doing soon. So before that, let us try to implement a similar clock tree buffer at this point as well. Let us try to do that first. So at this particular node, we'll break the node and we'll try to insert 2 buffers. So once we insert these two buffers, so this particular node will be driving this small length of wire and the input cap of these buffers, and these buffers in turn will be driving a pair of flop each. So now if you try to send the signal, send the waveform which is present at the input, if you try to propagate it through the entire clock tree, let's see what we get. So at this node you get a waveform which is very similar to the input. Next, if you propagate this particular waveform through the second buffer, the waveform is again is a good waveform compared to the previous one. So this is again a better one. And now the waveform which you see at this point, it is not now driving 4 flops, but it is driving the input cap of this buffer and the input cap of this buffer. So this is the waveform that you achieve at this node. And next, finally, at the final nodes of the buffer outputs, you see this kind of waveforms. So these are the waveforms that we expect actually to see at the flop and at the flop clock pins. So which is a better one. So we are actually seeing a waveform which is very close to the one which we had sent at the input. So what we'll do is we'll stop over here since I'm running out of time. In the next video, we'll discuss more about this waveform propagation thing, and we'll be deriving some more observations out of the clock tree that we have built, and see what those observations are all about, and that those observations will be the one that we'll be using to build a very huge clock tree for millions of flops. So these observations are important. So let us try to look all this in the next video. Thank you.